Okay, so we were looking at the convolution operation as a matrix vector product. Matrix is formed by this H. The columns of this H matrix are formed by taking the impulse response of the system and shifting it down by 1 unit every time. And then the X matrix is nothing but our input sequence. Now, there is an interesting way to look at this matrix product. In fact, there are two things that I want to say. You will see that this H matrix has a specific structure to it. If you look at its diagonal, it has the same element on each diagonal. So first diagonal is all H0, second is all H1, third is all H2, and so on. So this type of matrix in the linear algebra theory, it is known as Toplitz's matrix. Let me just write it down here. So this form of H matrix is called Toplitz's matrix. I should say this with this form that the matrix H has. It is called a Toplitz's matrix. Okay, this is something for us to note. It's not we are not going to get into the theory of Toplitz's matrices and all, but something that is interesting for you to look at. Now, what we are going to talk about next is not specifically to this H matrix. In fact, whenever you have a product of a matrix with a vector or a matrix with a vector, matrix with a matrix, you can have the same viewpoint that we are going to discuss next. But obviously we will be discussing this viewpoint in context of this matrix equation that we have written down over here. So the first viewpoint says that the way to look at the output of the convolution operation, which is this vector y, which we have seen in the previous slide, is this matrix vector product H times X, is to look at the columns of H matrix. H column 0, H column, this is a typo, I should correct it right away. Okay, it looks like I inserted this as a picture, so it's not allowing me to correct, but I'll say that this is actually HC1, not HC0, and so on. So you have HC0, HC1, and so on, all the way up to HC of 5, because there are 5 columns. And then this is our vector X. And now when you do this type of matrix vector product, obviously y is nothing but HC of k multiplied by X of k, which shows that the output is obtained by taking HC of 0 and then multiplying it by X of 0. This X of 0 is, remember, it's a scalar, so it either just stretches that vector or shortens it, but it can't change the direction, right? I mean, if you multiply any vector by a scalar, all that happens is you are changing the length of the vector, you are not changing the direction. And then same thing you are doing with HC1 and so on, by taking HC1 times X of 1 and all. And then you are adding all those vectors up, which means that this output y is nothing but a linear vector addition of all the column vectors of H. But remember, these column vectors of H are nothing but our impulse response after it is shifted down by 1 unit every time. And so what is happening is that the output that we get at the output of this system, the convolution operation, we can think of it as it is going to be restricted to occupy a space, a vector space. And that vector space is the one that is spanned by the column vectors of H matrix. And the reason is because of this particular expression. All that we are doing is we are adding a bunch of column vectors of H matrix. The only thing is that before doing the addition, we are either stretching or compressing each vector. How much we are stretching and compressing each vector is defined by this x of k. But ultimately, we are just linearly superposing all of these vectors. If suppose there are only two vectors, it will be just by the regular parallelogram rule of vector addition. But in otherwise also, you keep on adding the vectors using the same parallelogram vectorial addition method. And so therefore, what you get at the output, this vector y, at the output of the convolution operation, you can think of it as linear superposition of the column vectors of H. Now, there is another viewpoint where we are actually literally going to shift our viewpoint by 90 degrees. And therefore, instead of looking at the output of convolution as determined by the columns of H matrix, now we are going to start looking at the output as determined by the rows of H matrix. And so when we do that, we again write y as h times x. Remember, y is this vector, y0 to y8. But this, now I'm, instead of writing H matrix as a bunch of columns, I'm looking at it as a bunch of rows. And these rows multiply with my vector x. And now I'm taking the dot product of each row with the vector x. When I take the first dot product, I get y of 0. Second dot product, I get y of 1. Third dot product, I get y of 8. Y of 3. And the last dot product, I get y of 8. So you will see the difference between the two viewpoints. Here, I needed to expand out y, vector y, and look at it element by element wise. Whereas vector x, I'm just looking at as a vector. Whereas over here, it's exactly the opposite. I am looking at y as a vector. I don't zoom into each individual element of y, but x I have to look it as comprised of different elements. So there is a shift in the viewpoint. But more importantly, in the earlier viewpoint, we were looking at y as a vector obtained by linear superposition or vectorial addition of the column vectors of H. Whereas over here, what we are saying is that each element of this vector y is obtained by projection of x onto a row vector of H. It's almost as if we are thinking of this row vectors hr0, hr1 up to hr8 as forming axes of this multidimensional space. X-axis, y-axis, z-axis, and so on. And then we are taking this x vector and we are projecting it onto each of these axis vectors. Why am I calling that we are projecting? It is because when you take dot product of any vector with some other vector, you are actually doing the projection operation. And from your high school math class, you would remember that this dot product is nothing but the cosine of the angle between the two vectors times obviously the magnitude of the two vectors. And so therefore, a particular element of this vector y will have a high value if that particular row vector of H is aligned with the vector x in that multidimensional space. In the extreme case, if vector x and this particular row vector h r of n, they are 90 degrees apart, then obviously this dot product will become 0. So this is a quick review of the dot product in case if you are fuzzy about it. When you take two vectors, take a dot product between the two, this is the expression of the dot product. Dot product is always a scalar, and the value of that scalar is given by the, as I said, the product of the lengths of the two vectors, the magnitude of the two vectors a and b, times the cosine of the angle between the vectors. And okay, I think I have again a typo here. I'll just remove this. It's not, we didn't take n equal to 2 in the previous slide, but the message is clear that when this theta angle is 0, you get maximum alignment and the dot product value becomes maximum. When theta is 180 degrees, you get maximum alignment but in the opposite direction, and the value of dot product becomes maximum negative value, or one can say minimum value. And when theta is equal to 90 degree or 270 degrees, then this dot product becomes 0. And so that is another way that you can appreciate what is coming out of this convolution operation. So we took the convolution operation, and by looking at it in terms of matrix vector product, we are able to get some insight into what is going on when we do convolution. Now, there is another viewpoint which is obtained as a visual way of this second viewpoint, which is dot product based viewpoint. And this is a very fairly common way of understanding the convolution operation. And so let us take a look at it. Actually, I took next several pictures from this Georgia Tech electrical engineering course notes. You should go and visit this particular website, and it has some more demos that you can play with. Now, before we look at this visualization, what I want you to understand is that in this dot product based viewpoint, where we are looking at this individual rows of H matrix, you see what is going on when we wrote this matrix in the detailed manner is that this individual rows again have the same H vector, except instead of writing it as H0, H1, H2, H3, we are writing it in the opposite manner. It is H3 which comes here first, then H2, then H1, and then H0. It's almost as if we flipped the H vector and wrote it in kind of the reverse manner. And then every time we are taking dot product with this vector x. So when we took the very first dot product, only H0 will get multiplied with X0, and that will become Y0. Second time, before taking the dot product, we will slide this H vector 1 unit towards the right. And so now it will be y of 1 will become h of 1 times x of 0 and h of 0 times x of 1. And so on. We can keep on doing that type of visualization as we move along the rows of this H matrix. And so that is what is done here in this visualization. This here is the input. The input now doesn't have only 6 samples anymore, it has multiple samples. Looks like it has about 9 samples if I am not mistaken. And then this is the impulse response h of n, and it has this particular shape. And so remember we said that we have to first flip the h of n vector, and the flipped one is shown in the red here. And then in this convolution operation we have to keep on sliding this flipped h vector 1 unit every time. And so right now, this H vector is flipped and it is all the way outside of our matrix. So this is kind of, you can think of this almost as a negative row of the matrix, which doesn't make sense. And so obviously the matrix has nothing right now, and so uh, the multiplication, the dot product, or the individual elements of the dot product are all zero. Now this is where we are starting to get some meaningful output. This is the very first row of H matrix that we had looked at right here. Remember, it had only H0. Everything else was 0. H0 was getting multiplied by X0. That is what is being shown pictorially here. H0 is getting multiplied by X0. That multiplication is shown in the green. The result of the multiplication is the output of the linear convolution, which is this green line. This is the third row of H matrix. Remember, now this H vector has shifted by 3 units, and so the red is the H, the blue is the X. This is the individual products. When we do the dot product, we have to combine all these 3 green lines, the values of the heights of these 3 green lines. That will give us that dot product that we were looking at, and the result is shown over here. And so that is how we can visually understand the operation of convolution. We keep on moving along. As we keep on going down the rows of H matrix, this is what happens. Every time what is being shown is in the green, what is being shown is a multiplication, and then finally this final value is the actual dot product that you obtain after adding all those multiplied values. Okay, so we will stop over here, and then from the next lecture we will start looking at some of the applications of convolution.